Hey everyone, this video is about calculating the number of atoms in a sample of matter that's a molecule if you're given a certain mass. So for example, if you have a sample of aluminum hydroxide, how many atoms of oxygen are there in a sample of aluminum hydroxide that weighs 3.75 grams? Well, you can imagine that converting to grams or converting from grams to moles to molecules and then to atoms is going to be our general process here. I'm sure you're pretty familiar with going through steps 1, 2, and then to 3, but then how do we make that leap into this fourth step? I'm pretty sure you know at this point how to calculate the number of molecules of aluminum hydroxide, but how do we extend that to the number of atoms? Well, I'm going to make my pen just a little bit smaller here so that we have a little bit more room to work with. We're going to start with our mass, right? 3.75 grams of aluminum hydroxide. Now, the first step is, of course, converting our mass to moles using the molar mass of this substance. If I add up the mass of one aluminum, 3 oxygens, and 3 hydrogens, I end up with a molar mass of 78 exactly grams per mole. Notice how, because the grams are written on the bottom diagonally, they will cancel, leaving me with the moles of aluminum hydroxide. Now, this right now is the moles of aluminum hydroxide, not the number of atoms. And I do one simple additional step, which is recognizing that in 1 mole of aluminum hydroxide, I actually have 3 moles of oxygen atoms. And that comes from this 3 here, which gets distributed to both the H and the O. And then my last step would be, and I'm just going to move it down here a little bit because it's going to be too hard to see on the screen. I'm going to draw my next conversion factor. And what I want, right, is the moles of oxygen to cancel. And what I want, based on what the problem has asked me, the number of oxygen atoms. And here's where I fall back to, yeah, that's right, Avogadro's number. Because there are 6.02 or 6.022 if you're going to use 4 sig figs times 10 to the 23 atoms of oxygen in 1 mole of oxygen atoms. And of course, if we were looking at molecules, Avogadro's number doesn't change. If we were looking at any object, anything that can be counted, there is always 6.02 times 10 to the 23rd entities in that group. Next, of course, is to just do the calculation using my calculator. And I take the number 3.75, I divide it by 78, because 78 is a denominator, times 3 times 6.02 times 10 to the 23rd atoms, and I get this long number on my calculator, 8.68269, and it keeps on going, times 10 to the 22nd. Now I look back at my problem and I notice that my starting value, my mass, has 3 significant figures. My molar mass for aluminum hydroxide 78 has 4. Now it looks like this third step, 3 moles of oxygen for every 1 mole of aluminum hydroxide, really only has 1 sig fig, but that's misleading. Those numbers were achieved by counting, and I know with infinite degree of confidence that there are in fact 1 aluminum, 3 oxygens and 3 hydrogens in that molecule, so I never use mole ratios to limit my significance when rounding my final answers. I could have written that 3.00000 infinity divided by 1.000 infinity, right? And then lastly, I chose to use a 3 sig fig Avogadro's number. If I had noticed that my initial starting mass was more than 3 figs, I may have gone and used 6.022, but for now, I just stuck to 3 sig figs, so now I'm going to round it. I count from the right, 1, 2, 3 places, and that 8 is the third place from the right, because I know, right, the first 8 is my most confident number. My second is a 6, my third is an 8, and I realize that this is going to be rounded. After my 8 is a 2, so of course my 8 does not get rounded up to a 9. My final answer will be 8.68 times 10 to the 22nd atoms of oxygen in my sample. If I look at this number and then go back and I look at the formula for aluminum hydroxide, because the number of hydrogens is the same as the number of oxygens, this would also be the number of hydrogens in my sample. So I could also extend this and do all of them and say 8.68 times 10 to the 22nd is also the atoms of hydrogen in my sample, because in aluminum hydroxide there are 3 O's and 3 H's. And then my actual value for the number of aluminum atoms, because I now calculated this number to the number of oxygens, I would actually divide this number by 3, because there's 3 times the amount of oxygens as aluminums. So my answer for the number of aluminum atoms is, I'm going to divide that number by 3. So 8.68 times 10 to the 22nd divided by 3 is 2.89 times 10 to the 22nd atoms of aluminum. I didn't have to do these other steps, but I extended it so that you could see how they would all compare. That's all for now, folks.